Now, previously, we know that we are studying control volume analysis. So we have done the continuity equation, and now we are at momentum, linear momentum. Okay, so we are keep looking at this equation. Okay, we keep looking at this equation, which is your linear momentum, the rate of change of your linear momentum. This integration part is your linear momentum, but divided by time, it become a rate of change of the linear momentum plus the rate of change of momentum in the control surfaces dimension. So you have a CV and CS equal to all the force equal to 0. Now, by now, you should already understand why the left-hand side can equal to force. Okay, because we are deriving from second Newton law, F equal to ma. Okay, so by concept, you should already know how to explain this equation. Okay. All right, so let's look at the application of this equation again for today's lecture. So we'll go through a few more. And if we not manage to finish all the slides here, I will just ask you to go home and read the slides. And then if you have any question on the example, then you let me know. Okay. However, all the steps are there. Okay, let's look at this example. Okay, this question is available in a tutorial question also. So if you already download, you can see this question. Right? All right, so let's look at your screen. So at your screen, you're having a diagram inside below your screen there. Correction on the diagram. The temperature is not R, but it's a Kelvin. Same with this one. So when I edit the photo, I accidentally typed the wrong unit for the temperature. Okay, so when you read my slides later on, these are the correction for the diagram that I use. I mistakenly put R for the Kelvin for temperature. All right. If you look at the diagram, we're actually having a pipe, and normally when you deal with control volume analysis, the first step you look for is your control volume. Then you need to know where is your input, your in, okay, and your output. Look for all this information when you solve problems, and you copy. If the question already give you the control volume, then you just copy this diagram into your answer. You get 1 mark for the diagram. Okay. Yeah. Then the next one, you look at the velocity, in and out, and the reaction, the pressure, and the area. So in this one, I already converted the pressure plus the multiply by the area, you get forces. Okay, when it comes to test, it will not be this direct. I will just tell you the pressure, and then I'll tell you the cross-section area of the pipe. Then you solve for the force. Okay. So let's look at the statement, problem statement, so that you understand what it's talking about. So we have an airflow steadily. You have a steady flow. So you should know what's going to happen in your equation later on. You have the steady flow. Between two cross-section, which is long and straight. So you have a long and straight portion, which means the area doesn't change. And cross-section is given, the length is 10 cm. Inside diameter pipe indicator like this one. Where uniformly distributed, another keyword here, uniformly distributed means you have a steady flow again. The temperature is uniform and the pressure also uniform at each cross-section. Okay, so what mean by uniform? It means that when you study early, you are seeing this diagram. You have an arrow with the same length, and you're seeing this kind. So this one means uniform flow or uniform pressure or uniform temperature. Okay. If average air velocity, the word average, it means that you can use the V hat. Okay, the V hat. And we already discussed previously, when you have an average velocity, the maximum will always happen at the middle of the pipe here. Okay, you have your U max here. So if you don't understand why this one U max, go and refer back to the previous lecture. Okay, when we talk about the conservation of mass earlier in the previous chapter, or not chapter, previous section. Okay, so you are given all the information regarding what is happening to the input. Input is 300 meter per second. No, sorry, section 2, it is here. The velocity at section 2 is 300, so V2 is given. And at section 1, must be, the word must be is, you need to comply, V1 equal to 70. So there will be a changes of velocity, as you can see here. V1 is lower and V2 is faster. So something happened to the system. Assume uniform velocity distribution at section 1 and 2. So something happened to the system. You need to determine the friction force. The friction force exerted by the flow on the pipe wall in section 1 and 2. So there's a Rx there. Rx is the friction flow. Why you know that Rx is a friction flow? Because your flow is going from left to right, and friction always against the flow. So Rx is a force that go against the flow of your water. Okay, not in this case you have air. The medium is air, so be careful when you look at air. You need to be careful. Something you need to be careful because air is compressible. You're able to compress air. The previous one, if you see water you can assume incompressible. However, if the medium is air, it is compressible. Okay, when it's compressible, you need to be careful on the thermodynamic property. Okay, so this is an example where you need to recall what you learned in your thermodynamic 1 and 2. Okay, then the next one, you need to refer to the reference axis, which is the y and x here. So all the parameter that go to x direction, which is to the right, is positive. If the force going up is positive. Okay, so make sure you clear. Again, correction on my diagram here. The temperature is not R, but it's a Kelvin. It's a typo error here. Okay, let's try to solve this question. We need to find the friction force. So the first one is to see where is your control volume again, which is a red color dot here on your right hand side of your screen. And then we need to know what is our force and fluid velocity. So this is the first step every time you solve for control volume problems. You look for your CV, control volume. You look for your forces. Which is most of the time you need to convert pressure to forces. Okay, you need to convert pressure to forces by using the products of pressure times area, and it's a cross-section area. Fluid velocity, you need to check. All right, in this case, fluid velocity is given in the statement just now. V1 and V2 is given. In this case, although the question doesn't mention, you can ignore the weight of the air. But normally, if you deal with air, you have this assumption because air is too light already. So the gravity doesn't act on the molecule of air. It's act lah, but the effect of gravity is very, very small compared to the water or something with a high mass. Then you have a gravity force like water. Okay. In for air, we can ignore in this case. Then already explained already, the Rx is your friction force. So we need to determine the Rx by using the by using the linear momentum equation. So recall your linear momentum equation, like what you see on the screen. So write properly the equation. So the equation will be CV plus CS equal to all the force inside the control volume. And be careful when you write, don't confuse with the continuity equation. This is a linear momentum equation where you have a volume here and the velocity here. And also the velocity here, v dot n hat here. So when you write, please write carefully in your answer. And the first one will come with the delta t. Okay. So this, you write this equation in your answer sheet, you'll get 1 mark for this equation, that telling me that you understand what is linear momentum equation. Okay. So the next point that you can score is that because the question already tell you that you have a steady flow, so the equation itself gives you 1 mark, and you draw an arrow, put at 0 equals 0 and write steady. This combination give you another 1 mark to know that to show that you know that what happened to the steady flow on this linear momentum equation. Okay, so if you accidentally you just cancel with arrow and do not give me this one, do not give me statement, then I will just put a question mark in your answer, and you will lose this 1 mark in your answer. Okay, so it's easy to score, but also is if you careless, then you will lose some marks there. Okay. Any questions so far? Any question you want to ask me on step 1 and step 2? Anything that you're not sure what is happening on the screen? Again,
No.
No, okay. Yeah, okay. Temperature is Kelvin. Okay, next, then you look at the screen. Pull the equation up. So because the control volume side already cancelled, so you only need to solve for the control surfaces component and the force. Okay, the forces actually you just read from your free body diagram. Okay, with all the force here. So you know that from the free body diagram, you have 3 forces on the right hand side. You just pull to the right hand side and comparing to the axis that you have. Okay. So I just put the answer on the screen here. So the forces, you can have the first one, negative Rx. You should know why this one negative. It's because your X direction is positive to the right hand side. So your Rx arrow is pointing to the left. So you get negative sign here. And you have for section 1, there's a pressure and the area product give you the force because of the pressure. So P1 P1A1 give you forces. Is positive because it is from the left to right, also along x-axis. However, for the left hand side, you're having a pressure that pointing to the left hand side, you get a negative. Okay, I repeat this one, I think for the third time or fourth time already. If you look at pressure always pointing to the area. Pressure force always pointing to the surface. So that's why we can draw this arrow pointing to the left. Okay, what is going to happen in your test later on or exam? You're not going to see the pressure arrow. Okay, you're not going to see the pressure arrow. I will just label this one as your input or 1. I'll label this one as 2. And then in the statement, I will tell you pressure equal, for example, 10 megapascal Point 2 give you pressure at point 2 in the statement. Point 2 equal to 100 Pascal. And you convert to the force. I'll give you the cross section of the pipe A. So you need to smart enough to convert between forces to the pressure to the forces. So again, I will expect you to know how to draw the free body diagram by adding this arrow, okay? Pressure will acting on these two, and of course there's a if you say there's a forces on this one or not, yes, there's a forces, but this y component is too small, so we can ignore, okay? Because the flow is from the left to right, so the pressure have no time to act on the surfaces, but the surfaces is having a friction force. That's why it's slow there's something happened to the velocity, right? So I already explained the force component, y positive, y negative. So the next one, I'm going to explain how you solve for the left-hand side. So left-hand side, you start with the V. So you have point 1. Point 1, you change the V to U, it because your flow is to the X direction. So and it's positive. Y positive because the velocity direction is from the left to right that you see on the diagram here. Okay, that's why you get a X direction here and positive. Okay, X direction. So then the next one also same. This one for your U2 component, you also get positive sign because the velocity is coming out from the right hand side. So also positive because it's go along the x-axis. Okay, so be careful. In test, I might change this one to Z. So when you're having a Y and Z component, this one you need to use W. This one also need to use W if your reference axis is Z. Okay, if the question already changed the axis to Z, in your answer you use U, put a question mark there, and I will not proceed to mark anymore. You have no more mark for the remaining question answer. Okay, so take note on this one. These are the trick point where I will test your alertness in your test. So if you still continue to write U in your answer when we change the axis, I will put a question mark there and you lose mark for the remaining answer. Okay, means that you don't understand what is happening in the question. Take note, these are the area where students make mistakes. Then I already explained about the U. Rho doesn't change, but however, the products of rho VA or rho AV that you learned in the first session, rho AV give you m dot. However, this component is come with a vector with the n hat. What does it mean? When you have an n hat, you need to look at inlet or outlet. So don't confuse this concept with the continuity equation. We are now at the linear momentum, where I already explained what happened in your inlet. Your inlet always negative. Outlet always negative, always positive for linear momentum for your outlet. So that's why here you are seeing negative sign for m dot because it's an inlet, and you have point 2 is your outlet. That's why your m dot here is positive. Of course, in your answer, you can continue to use rho AV. You put negative rho AV here, positive rho AV here, also correct. Okay. Take note on the direction there. Okay, and also when it comes to test, it will not be that direct. I will flip the diagram. The flow might be go from the left to right or right to left. Okay, so don't just memorize the steps and not understanding the procedure. Okay, so again, from continuity equation, you know that the m dot is the same because you have all the steady flow stated there. So the m dot will be the same. Okay. So rearrange the equation. You manage to find what is your Rx. If you rearrange the equation, you manage to find the area times P1 minus P2 and minus m dot U2 minus U1. Of course, if you don't do the factoring also okay. You just write rearrange the equation Rx on the left hand side, the remaining component on the right hand side. Okay, so far we're still at a mathematics model. Doesn't link with the control volume analysis yet. Yeah, a bit, but not much. Okay. The next is just substitution. What is important here is that in this case, because you want to find the m dot equal to rho AV. In this case, you're not able to find the rho because the rho is not given and it is air. So that's why you need to recall your thermodynamics understanding or chapter to find the rho by using the information of pressure, temperature, and Rankine number or gas constant number. Okay, so gas constant for air is 287 joule over kilogram Kelvin. So this one I will give you when it comes to test or exam. You will have a table at the last page of your exam paper. You need to refer to that particular temperature. Then you have the R value. Okay, so in this example, this tutorial, we will use a gas constant value of 287 joule over Kelvin over kilogram Kelvin. So from what you learned in thermodynamics, you have an ideal gas equation here. Rho equal to P divided by R divided by T. Rho equal to P pressure divided by gas constant times the temperature. So you manage from the pressure, temperature, and gas constant. You manage to find what is your density. Okay, so this one is something that you need to recall from your thermodynamics. Area, you need to I expect you already know how to calculate area of a circle. Okay, pi r square or pi d square over 4. You can use whichever that you are convenient to use. Same, you reach the same answer also. So from here, you manage to find what is your m dot. M dot equal to rho AV. You use the second one, rho 2 A2 U2. You manage to find what is your Rx. So I'm not giving you the answer of the Rx, but I'm showing you the steps how you solve for Rx. Okay, ask me question if you're not able to follow or not able to understand what is happening. Okay, everyone good, huh? All right. Now there's a side note for this example. So there's a differences between compressible and incompressible. So if you have a compressible case, which is in this example, you're having a compressible flow because you're having an air that's able to compress. So you're seeing the velocity is accelerating inside the control volume. Okay, so there's if you being told to calculate the acceleration means you take the velocity divided by time, you manage to find the acceleration. However, in this example, it's not being asked to find. Okay, so and also from the momentum also, you know that mass flow F equal to ma. So from this side, you already find from the answer already, because this one you calculate from the integration of CV and CS just now. You already cancel the CV because you have a steady flow, and you calculate the CS just now, the control surfaces component just now. When you equal to force, and you're given the mass of the flow, the air, you manage to find the acceleration inside the control volume. Okay, so just as a principle, you should able to explain what happened if you have a compressible scenario. There will be a change of velocity magnitude inside the system where you have an acceleration happening. If you have an incompressible case, then your velocity will be the same. There's no change of velocity inside the pipe. You will result the pressure change together with the friction force. Okay, the key difference is the velocity magnitude. If you are compressible, then you have acceleration, meaning the velocity inside the system will increase. However, if you have an incompressible, then the velocity 1 will equal to velocity 2. There will be no acceleration of the velocity. Okay, so take note on this. This will be an important concept when it comes to your final exam, or maybe in your assignment later on. You need to explain it based on the answer. You need to compare whether what happened if it is a compressible or incompressible case. Okay. All right. We go for one more example, then we go for a short break. Okay, we look at one more example before we go for a short break. I'm going to go very fast in this one. The concept will be the same. So what you're having here is that if you look at the diagram here, if you look at this diagram at the lower corner of your screen, so you're having a pipe also. However, this pipe is not having a steady flow or uniform flow. As you can see from section 1, which is your inlet, you have a uniform flow here. And when it comes to section 2, you're having a parabolic shape of flow. And in the previous section, when we study about continuity equation, I already explained how do we convert the parabolic flow into a uniform flow already. Okay, so I also explained the equation that you see on the screen here. So if you're not clear how we convert the non-uniform flow in parabolic into a uniform flow, go back to the previous lecture and re-watch the video or revisit the PowerPoint slides for conversion from non-uniform to uniform flow. Okay, so in this case, we're having a pipe and you're having a radius from the center, and our reference point are from the center of the pipe. The R is the intrus radius and the R is the outer radius. Okay, R is means from the center to the wall here. Okay, and I also explained about what is dA, the change of how you calculate the area by using 2 pi r dr in the previous lecture. Okay, so you can find the area by using this equation. Yeah, what else? So your velocity at point 1 or your inlet is U, capital U. Your velocity at point 2 is defined by this equation, U max times 1 minus R divided by R square. All right. So the question tells us that you're having a incompressible case, laminar flow water. So at section 1, uniform velocity. Section 2, you're having a parabolic flow. And in this case, I already tell you is maximum at the center. Okay, consider flow now is a Okay, so this statement is for the diagram that you see at the bottom. Now it asks you to consider another scenario where you flip the orientation of the pipe now. The pipe now is vertically upward. It means that the flow is flowing from below, go to the top here, and the axis is given in the diagram on the right hand side. Okay, so what does it mean? It means that this one, if this question come out from the exam, this diagram will not be given. The diagram on the right hand side will not be given. We will test your intelligence in using what you see on the screen and convert to the real scenario that to solve the question. Okay, so be prepared for this kind of question. We will just give you a general diagram and then we'll give you a statement, something like this, that what you see on the screen here. We will ask you to consider, after we give you a general statement, we will give you a scenario. We will ask you to consider at a certain orientation. In this tutorial question, we ask you to consider a vertical upward direction. So we expect you to know how to draw the diagram. So there will be one particular section that asks you to sketch the flow in vertical. So we're expecting you to draw the first one, control volume. Means you trace the red color into a new diagram. Second is your inlet. Second steps, inlet and outlet. Yeah, first step, control volume. Second, inlet, outlet. Third, you need to convert your pressure, or you can draw the pressure, not pressure, velocity. Fourth, draw the velocity at both ends. Mark your flow direction. Then convert the pressure into forces. Okay, start from step number 7 is the force you put inside the force. So step 7 is you convert forces, you convert pressure to force. So this one, step 7, inlet and outlet here. Step number 8. Okay. So again, the pressure here is pointing into the area here. Okay, I already explained how pressure act on area or surfaces, always pointing to the surfaces. This is how pressure act. This is a very fundamental concept. If you have pressure, pressure will act on to the surface at 90 degrees. Okay, 90 degrees. Yeah, so these are the area that students make mistake, especially on the outlet. No issue on the inlet. All students know how to draw the inlet, but there will be 1 or 2 students that they will forget when they draw, when they convert pressure into force, they forget the direction already. They will draw this force going out, and then you get the wrong answer. Okay, the next one, you will consider the weight of the fluid because you're using water. Water always comes with a mass. Mass will always give you weight. So this is the number 9 steps. Okay. And then you read the question. The question asks you to express the fluid pressure drop that happened in section 1 and 2. So in this case, you having a friction force also. So you need to consider the friction force of the velocity of the fluid. So this is step number 10. You will see RZ, Y is pointing to below because your flow is flow from below to top. And friction always go against the flow. So this arrow also one of the area where student will miss it in the answer. So remember, friction force, when you have a fluid like water, you also need to consider the mass of the weight of the water and the friction force inside the system. Friction force always go against the direction of the flow. So if you flip the diagram, the force will go from the pressure is the velocity direction is from the below to the top. So that's why your RZ is pointing down. Okay, I've done explaining about the diagram already. So the next is just application of the equation. So we have done explaining about the control volume, explain about the force, about the velocity. The next one is just application of your linear equation. So I don't need to explain anymore on this equation. So as usual, you add this arrow, write 0, steady, straight away, give you 2 marks for this effort. Okay. So you rearrange, you rearrange, and then you reach this stage where you have an integration of your control surfaces, V rho V dot N hat. Write properly in your answer is an N hat. N hat is a vector unit, like what you write in for your physics class. Your I hat, J hat, K hat is the same. Okay, so if you rearrange, you write this equation, you get another point for simplified equation, this one. Okay, the next you solve for the force, like what you did in the previous example. You solve for the force. This one you read from the free body diagram. You have the pressure force in and out. Okay, you should know why this one positive, why this one negative. You should know already. If you don't know, go and watch the video that I explained 10 minutes ago. Rewind the video, watch again. Okay, and here there's a friction force. I already explained why friction force is negative. Look at the axis here. Okay, the weight of the water also negative because of the direction going down. Okay, the axis Z positive going up. Y to the left is positive. Z is this direction. X is toward this direction. Okay. Stop me if you're not able to understand the positive negative sign for the force. Then I want to stress on this one. This is another example when you convert the V from the general equation here. In this case, you are looking at Z direction. That's why you are using W. Again, in test, if you accidentally write your answer U, I'll put a question mark there. I will no longer proceed to mark your answer anymore because the rest is wrong already. Okay, so if you write U, if you in your answer in this tutorial question, if you write U rho V dot N hat dA, although the force component is correct, I will just put a question mark in your answer. I will no longer proceed, okay, to mark your answer. Okay, because the rest is wrong already. It means that if you write U, it just tell me that you don't understand this formula. Okay, you don't understand what is this, what it is, what it is. Okay, so I don't need to continue to mark your paper anymore. Okay, so I explained about the positive negative just now. And this line is extension of this section. So this one is section 1 or your input. This one is your section 2. Okay, before you continue, you should know the positive direction. Your W1 is positive because it's going in and along Z-axis. Here also, W2 also positive because it's flowing out. This is your W2. And it's go along Z-axis. That's why positive. Then also this is the area where students make mistakes. The first section is actually, you need to be careful. Your m dot is referring to input. M dot, when you look at linear momentum equation, input always negative, output always positive for m dot. So that's why, if you can see on the second section here, when you integrate area 2 rho AV, because this here to here is your m dot 2. Okay, m dot equal to rho AV. So your V here also is W. So if you accidentally write U in the answer, I will put a question mark and I'll stop marking. Okay, so I'll be very strict in all this notation. Be careful when you write your answer. All right. Then the next one, why in the second section we need to use the dA? Why there's an integration of dA? Because in section 2, you're having a parabolic shape of velocity. That's why you need to integrate your answer here. Okay, the rest is mathematics. You rearrange. Okay, so this, I put it here, just a step of mathematics. When you have integration, you just see whether you can simplify or not. In this case, you can, because U2 and U2 become U2 square. Rho is a constant value you pull outside. That's why you get the rho outside, the integration. The A square. So in this case, because area is not given, you need to convert the dA in terms of dr. Because the area here is not given, you need to smartly use the dr equation, because dA equal to 2 pi r dr. And we've seen this kind of question before in the first session when we deal with continuity equation. Again, if you're not clear how to convert dA to 2 pi r dr, go and watch the first session, the previous session for the continuity equation when we deal with parabolic flow. Okay. Then you substitute the equation for the V. So there's a change from on the notation, W2 just now, and this one is W1. Okay, there's a changing of notation. W1. It's not W2. So when you solve this kind of question, take note on the important notation. This is W1. Okay, why you use W1? Also, go back to the previous lecture. I already explained why you can use W1 here. Okay. Then the rest is just substitution and your mathematics skill you need to pull in where you do the integration. Okay. So integration, you'll get for A2, you get this answer, 4 pi rho W1 square R square divided by 3. The rest is just mathematics, rearrange. You'll get the pressure different because you want to find the pressure drop. Pressure drop is, you need to look for P1 minus P2. That's why at the end, you need to rearrange P1 minus P2 equal to the rest of the equation. You get this one. Okay. So I just put a side note for you. At the end, you'll get this form. P1 minus P2 equal to this form plus this form plus this form. So the first one is about momentum flow. The second one is because of the friction, wall friction, RZ. The third one is because of the water weight, or we call it hydrostatic pressure. Okay. So in test, I'm going to test you whether you understand what is the equation or not. So I will give you a scenario. What happened? I change the flow. If I increase the W1, what happened to the pressure? If I increase the area, what happened to the area pressure? Okay. If I increase the pressure, I remain the flow velocity, I remain the area, I remain the water weight. What happened to RZ? You have to know the relationship from here. Okay. So what happened? Yeah, if I change some of the parameter, for example, I increase the area, what happened to all this? If some of these parameter I remain constant, what happened to one of them? Okay. Important, you need to understand what is this mean. The first one is momentum flow. Second one is the friction. Third one is the water. Okay. Now, so this one is just explain what caused the pressure drop in the pipe. You have three components to solve: momentum, wall friction, and the weight of the water. Okay. So the next question maybe you can think about is, if the velocity profile is identical means section 1 and section 2 is identical, what happened to the pressure drop? Okay, so there's an answer there. So if your flow rate is the same, the velocity profile is the same, identical, means whether your inlet is uniform, for example, uniform flow, and case number 2 also uniform flow, you can cancel the first one because momentum flow is the same. Or you have a parabolic flow, same equation apply for section 1. Section 2 also parabolic flow. Then you can cancel the first one because change of momentum is the same. There's no change of momentum if you're having an identical flow. We call it fully developed condition. Okay, something new for today. If you have an identical flow profile or velocity profile, whether it's uniform in and out or parabolic in and out, you're having a scenario called fully developed flow. And fully developed flow, you can cancel the first one because there's no change of momentum inside the flow. Okay, then you only need to process the wall and friction wall and the weight of the water. Okay, so there will be a section ask you about this one. Okay, there will be a section in your test or final exam. They will ask you to explain or give you the scenario why or what happened to the wall friction and the weight of the water if you're given so and so scenario. Okay, actually you are playing with this equation. All right. Another possible question will be what contribute to the pressure drop if no is additional to being fully developed, the flow involved if you ignore the weight. What happened to the pressure? Okay, what happened? Okay, you need to think about this one. By looking at this equation, what happened if you ignore the wall friction or we ignore the weight? What happened to this pressure? Compared to two scenarios, one with all the effect considered, one is with either one of the effect is ignored. What happened to the pressure flow? Okay. Okay, so if you have a same velocity profile and you have and ignore the weight of the water effect, then you only need to consider the wall friction only. Okay, I stop the recording here. Okay, I overshoot the time.